The last geometry we have to look at is the square planar. And it becomes instructive or more obvious to compare the square planar and the octahedral complex. So we're going to do that again with a new geometry. So in this case, we're comparing an octahedral complex versus square planar. When we compare these two geometries, our octahedron has a transition metal center that is surrounded by 6 different ligands. Our square planar complex is only surrounded by 4 ligands, and they're essentially the same shape, but along the z-axis, which is straight up and down right here, there's no interaction between the ligand and the transition metal along the z-axis. And because of this, this is going to influence the d orbital splitting. And the way it's going to influence this is that any orbital with a z component will lower in energy. And the reason it lowers in energy is because it has a weaker interaction. So how is this going to influence our splitting diagram? So we can draw in for an octahedron our T2G and our EG orbitals. And I'm actually going to label each of these as XY, XZ, and YZ, and x squared minus y squared, and z squared. So anything with a z component is going to have a weaker interaction. So our dz squared orbital is going to drop down fairly low in energy. And our dxz and yz relative to an octahedron will also drop down in energy. One of the things that we're also going to observe, and in octahedral complexes and in square planar complexes, there's something called symmetry elements that put kind of restrictions on what can happen. In the case of the octahedron, you have 6 ligands. All of those ligands have to have very specific bond angles. And if we define the molecule as an octahedron, all 6 of those ligands have to have the exact same bond length. And they're going to find kind of an equilibrium where it's going to get the optimal bond length to lower the overall energy. In a square planar complex, the metal and the ligand have to have the same bond length, but we only have to deal with, if I'm a ligand, it would be myself and 3 others. So what happens is we typically observe different types of bond lengths in each of these complexes, and as a result, anything with an x and a y component gets shoved up in energy a little bit. So if we look at the crystal field splitting diagram for a square planar complex, we're going to have the xz and the yz at the lowest energy, followed by the z squared, followed by the xy, followed by the x squared minus y squared. So, and this really kind of isn't drawn to the best scale, but due to the large difference in energy between d orbitals in a square planar complex, the square planar always gives low spin. And there's a specific case that we typically see for most square planar complexes, and that's that they're D8. If you look at what happens in a D8, we fill up these electrons up to this level. So typically, we don't fill the electrons all the way into this x squared minus y squared orbital because they're really, really high in energy. And ultimately, a transition metal complex is going to pick a shape that it wants to adopt that's going to give the lowest overall energy. And when we get that low energy configuration, we find that this happens when we put a D8 transition metal complex with something else that can cause large splitting in energy. That something else is either a strong field ligand or a 4D or a 5D transition metal. So this is where we get those observations and the criteria that I gave you to try to identify which complex will form a tetrahedral environment and which will go with square planar. So one of the things that I want you to always keep in mind, and the overall theme that we discussed through this entire chapter, and when you're doing the homework problems and studying for the exam, make sure you keep energy in the back of your mind and the d electron count. Because these two topics and these two concepts will help you analyze all of your different transition metal complexes. So you want to keep that in the back of your mind. All the properties, the color, the magnetism, all the great properties of these transition metal complexes center around these two guys right here. So I'm going to wrap it up for this today. I hope everyone has a great weekend, and I will see you on Monday.